I don't have to reinvent it, invent it or reinvent it, it's already. But people are usually not doing conformal gravity the way I like to do it. So let's again look at that Einstein-Hilbert explanation. I say L is 1 over, I think, I almost forgot the coefficients here. Over 16 pi g, and then there's the square root of minus g, and there's the Ricci scalar here, and then there is plus square root g, and then the L of matter. The L of matter contains g nu as well, of course. This is gravity, the Newton's constant downstairs, and this is the matter Lagrangian and Schur. Together, the matter Lagrangian is an entire standard model, whatever it is. Now, what we can do now, let me write G nu, which depends on space and time, I'll just write it this way, is, by definition, an omega squared of x times G nu hat. I split up degrees of freedom. G nu hat has a constraint. For instance, I could put determinants of G nu hat equal to 1, or minus 1 rather. If you put determinant of G nu hat minus 1, then if this determinant of G nu is not minus 1, then I put all the remainder into this coefficient omega in front. I put the square just for future convenience. Now let's look what Lagrangian looks like. And so basically, the function integral will be dg will be translated to a function integral of omega and a function integral over g hat, with the constraint that whatever I impose in g hat. Actually, the constraint I impose in g hat is a gauge choice. I can choose g hat any way I like, but I just make a substitution. Then Lagrangian looks like this. L is square root of minus g, better put it in front of everything. There will be 1 over 16 pi g times omega squared r. And that will be a plus 1/6. Actually, 1/6 can be seen in n dimensions to be 4n minus 1 divided by n minus 2. But that's in n dimensions, but let's stick to 4 dimensions. Then there's g mu d mu omega, and that all multiplies that, and then there will be plus the L matter. And the L matter depends on omega and on g mu hat. And what is now natural to do is, first of all, to rescale omega. Oh, this 1/6 is a very important 1/6. It happens in many conformal symmetries. What I can now first do is rescale omega. It's not so important, but I'll rescale omega by some coefficient kappa. And if I rescale it, then this Lagrangian will look like 1/2 g mu hat d mu omega plus 1/6 times some coefficient times omega squared r. Basically, this, I think it just goes like this. And then r hat, that is the I generated by the g hat. And then there's the usual element. Now this looks very familiar. This is just Lagrange on a scalar field with a 1/6 omega squared, sorry, 1/6 omega squared r hat added to it. But that's also quite conventional. People often add a 1/6 r times omega squared to the actual scalar field so as to get the whole expression conforming. Then if I now multiply omega by a constant, lambda omega, then this whole expression just scales in a beautiful way. So that if I scale g hat by some vector omega g hat, and omega by, I think it has to be that divided by omega, that's a square here. If it makes such a transformation, this Lagrange is invariant. And this I would call a conformal transformation, but a local conformal transformation. This omega may depend on space and time. So this makes this omega field just a scalar field, and that scalar field transforms in a non-trivial way by conformal transformations, and it's completely.
Excuse me, don't we have g hat under the square root?
Sorry?
G hat under the square root around the red line.
This is g hat. Was that the question? Yes. So this is a rewriting of the Einstein action and the meta action by saying everything is now conformally invariant. If I take the g hat metric, I can trivially multiply g hat by the omega squared and divide the omega by omega squared. Of course, that leaves this expression invariant. So this is a very trivial conformal transformation, because the real physical depends on this window, which is this product. So if I multiply this by the omega squared, divide this omega by capital omega, of course that's an invariance. So this theory is obviously conformally invariant. But now let's use the language of gauge symmetry and say it's not only conformal invariant, it's also spontaneously broken. And that's because the vacuum excitation value of omega is some function which contains something like the square root of Newton's constant downstairs. If you do things precisely, I just rescaled omega. So doing that, I get some number. So this is just some number, call that f. That's the vacuum excitation value of omega. So this is a way of rephrasing ordinary Eisenhower gravity in terms of theory where conformal stability is spontaneously broken. This is just a field, and the field is vacuum excitation value, and everything goes through it as before. I haven't changed a thing in my physical equations. So this is just ordinary Eisenhower action. And displaying a kind of hidden conformal stability. Why hidden? Well, spontaneously broken. Why didn't we know it before? Well, it's badly spontaneously broken. This number f is very large, and usually it has the effect that you don't see conformal stability at all. Just like in the weak interactions, when people wrote first down a family interaction for the weak interaction, this is a four-family interaction, nobody saw any fantastic local symmetry in that. And that's because the local symmetry was there, but you have to first introduce the W boson and Z bosons to see the local symmetry and to say that there's a scalar field which has a large vacuum excitation value. It's just the same story all over again. This symmetry is spontaneously broken. Conformal symmetry is potentially very important because it involves scale transformations. It scales you from large distances to small distances. Saying that symmetry is only spontaneously broken means that now I have perhaps a machine in my hands allowing me to make scale transformations in physics. We didn't have that before. The scale transformations may well play a very important role in understanding what happens at very high energies. If you manage to scale ordinary physics to very high energy physics, that may be a superb way to understand Hampstead High. We're not there yet, but for very good reasons. But this is a very promising way to look at things. Now, it's about time to end. There's just one thing I want you to ponder about. And that's the sign. This omega field here is like a scalar field, but it has the wrong sign. That's too bad. It means it isn't a scalar field, it's something else, it's something doing things in gravity. And so this theory is a nonsense theory anyway. If you put the wrong sign in the scalar field, then your theory is no longer unitary. Well, you might think that, but remember, I've done nothing physics-wise. This is the ordinary Einstein-Hilbert action, and the effect of omega the other side just comes out as a property of gravity. In fact, gravity is another strange force. The gravitational field has a negative energy density. So there's something funny about the sign in gravity. Of course, you could say that right away, gravity has equal things attracting each other, whereas electromagnetism has equal things repelling each other. That is a source of difficulty. So something in the sign. Well, wait a minute. Easy to help. I just replace omega. I write as I times the field eta, and all is fine again. Isn't that really too simple? Yes, if there are all directions over in other fields, if there are direct mass fields in my Lagrangian, I might have a problem with this transformation. If you replace omega by I times something, then of course I can change the sign here. This will be minus eta, and this will also be minus eta squared. Everything will be fine again. So don't worry, it looks like a very trivial thing to cure. However, if I change omega by I times omega, the vector excitation value is imaginary. Eta has now an I in it. So, or minus I. Eta is minus I times some big function f. That's very strange, perhaps, but you got to get used to it. That's the way it makes things work. But now, this omega field becomes just like a completely ordinary scalar field, in no way different from the Higgs field. Except in one thing. If this omega goes to 0, I'm going to the small distance limit, where people told me all the time, we don't understand anything. Well, what about the far field, the Higgs field going to 0? Is that the limit where we don't understand anything? No. The Higgs self-interaction is just a direction like this. I'm talking about this point. What's so enigmatic about that point? Nothing. The field just floats, and there's no singularity at this point at all, in terms of the Higgs field. But in terms of this omega, or rather this eta field, there seems to be a singularity when it goes to 0, because then I'm describing a metric tensor where omega goes to 0. Remember, I had here. And then omega goes to 0, the metric tensor goes to 0. I'm describing an extreme small distance limit. What's happening here? So, we have to say that there should be no singularity at very small distances. Let's impose an extra ingredient in the laws of physics, that there's no singularity if omega goes to 0. So let's say it here. This is my new contribution to the laws of physics. This we didn't know before. If you impose that, everything will change. And this will in fact also have an effect on standard model. Unfortunately, a disastrous effect, but I'll try to explain to you what happens if you make such an assumption. But that's for not tomorrow, tomorrow we'll do a popularity lecture. In fact, there will be a lecture about our lovely Higgs field, and not really about what happens in those 0. That's another question. But then I'll continue the day after by discussing this feature. This will change everything. So that's it for today. If I have questions, you're welcome to ask.
Thank you for your lecture. Any questions, comments?
If you, in the mapping of between, well now it's not there anymore, you're basically, between the black holes region A, region B, and so on. You used a point transformation, so G mu of x like omega G mu. Can there be something more complicated, like I'm thinking of a mapping of a space-time to a different beast, like double field theorem, maybe, or some sort of Born transformation, when you, so basically what an observer calls space-time, another observer would call winding number or momentum or something like that. And can this help in, of course the system would be much more complicated.
This is precisely the point I said about locality and causality.
Yeah.
You would mess up. What's locality for one observer is not locality for the other observer. What's causality for one observer will not be causality for the other
Only
observer.
causality, no, you can have a,
Well,
if it's a unitary
you'll have a very hard
if
time.
it's unitary transformation, then
You'll have a very hard time to understand what causality means for the other observer, because the light cones don't match. So when you mix up future and past for one observer as they are ordered for the other observer.
but
So
that's not
at least you have
transformation.
difficulty. I'm not saying that you can't just resolve it. Maybe you can, and you're much more good than I am. But maybe you can solve that. But I'm not able to do it, put any handle.
Well,
Have any handle to solve it.
one has to interpret things, but if I do everything with unitary transformations, then things may be it's a matter of interpretation. So in my space-time, it's different. Think of duality.
But you know, in
equality.
most branches of physics, we don't make transformations which mix up future with past. In a non-linear way. I mean, the type of those that's fine. Otherwise, what's future for one observer should be future for another observer. Unless you do something which is, well, beyond most people's ability, which is, you know, you say what's in the future, one observer is in present or in past of the other, and somehow we manage to prove that physical one observer is the same as the physical of the other. That will require a kind of magic that I am not able to understand. So I would like to leave that magic aside for as long as I can. So I just insist on having more visual, obviously identifiable form of locality and causality that I can work with. And that's what I've been doing here, and I see that that may be enough to do something important.
I think something much more down to earth. Think of ordinary quantum mechanics, a lattice and a particle on a circle. They are dual to each other, but what is the momentum in one is the position in the other one. But then, of course, but then both systems, quantum mechanics, are the same. So, and if you have an harmonic oscillator in the two cases, they are also dual.
In that case, I will not talk about integrable systems where life is still easy.
Yeah, okay, yes.
So suppose the system is not integrable. Then what would you be able to make such transformations?
Okay.
I would be very hesitant. I'm not saying it's impossible. Maybe someone will find a way to do it, but I wouldn't have some big clues about understanding such transformation if the system is not integral. I believe the entire world is probably not integral. Otherwise, this universe would be there for nothing. We could just integrate the whole thing out. But that's not going to be that easy.
Any more questions? Comments?
There's a question.
So, omega is a ghost in this case.
Well, you could call it a ghost. You could call the Higgs field a ghost. But you also know it's physically. It depends really how you fix the gauge. That you see in other theories as well. Think of all the quantum field theory where you fix the gauge either by fixing the Higgs field to be a real field in only one direction, isospin space, or you fix the gauge by looking at the vector potentials. What is ghost, what's physical is slightly depends on your gauge choice. So in this situation, well, of course you know if you make a coordinate transformation, your omega changes. So your omega depends on your coordinates, and say that your theory is independent of which coordinates you use, this omega may seem like a ghost. So if that's your definition of closed, it's closed.
I have a comment. I was asking.
So you, in your picture, the conformativity is broken spontaneously in the gravitational sector. We know that in the matter sector, the conformativity is broken by anomalies, in the sense that there are arbitrary values. Is there a connection between these breaking, or there are two different things in your picture?
My next lecture on this will be all about those anomalies. Because yes, you're right, the conformal transformation normally is associated with anomalies. In fact, the whole fact that the standard model obeys realization group equations with all these beta functions, all that is consequence of anomalies. And now I'm saying my theory should not have those anomalies. So the limit order to go to zero is completely upset by lambda ghosts and a whole lot because of those anomalies. Those ghosts should not be there. That's going to be the basic message next time.
So is dynamically broken by matter, conformal symmetry, or by...
Well, I don't know who is the agent of the dynamic breaking. It's just the interactions as such that omega likes to take the value f, but the value you choose that depends on what you chose your vacuum to be. If you choose a different vacuum, you find a different f. So, and basically it's all about doing expansions. You expand around the region that you like most. You say, well, that region is my vacuum, and now do an expansion around it. And then some other guy comes who happened to be falling into a black hole, says, that's not my vacuum, I'm doing another expansion. So, I don't know exactly what the question was anymore, but anyway, this is the picture of it.
I have last
There
comment.
was a question there.
In the Poincare theory, of course, the vacuum excitation value must be constant.
So indeed,
In the Poincare invariant theory, when you have a Poincare invariant vacuum, the vacuum excitation value, of course, must be constant. In gravity, I don't see a reason for this to be the case. I mean, can the vacuum excitation value of omega be some function of space-time?
well, the way I introduce conformal symmetry here, it's a local symmetry. So this parameter omega can be anything you like. But if you apply such a transformation, your metric tensor will no longer be the metric tensor of the vacuum. If you insist the metric tensor stays the same in the vacuum, you only have the thing people call a global conformal transformation. You can have x over 1 to 1 over x will be a transformation that, apart from anomalies, then will leave many laws of nature invariant. So Maxwell's equations, for instance, are invariant under x go to 1 over x. You have that particular conformal transformation just because you still want to stay to a flat space-time. Whereas if you allow space-time not to be flat after your conformal transformation, you can have it dependent on space-time in any way you like. Right? So that's the way conformal symmetry works. There are the special conformal transformations that transform flat space into themselves. That's very important for standard model where you exist in having a flat background, but you can still not make those conformal transformations. Then that's a limitation. But in the way I introduced here, omega can depend on space-time in an arbitrary way. The price I pay is I go from flat spaces to flat spaces. Well, that's what I want to do in the case of black holes.
Any more questions? No. I can, myself, just one observation that you cannot take the same discussion by taking the standard gravity theory. I mean, if you take instead of the Lagrangian, like Einstein-Hilbert Lagrangian f of r, some function of the, anyway, the relation between the Jordan frame and the Einstein frame by conformal transformation. So I don't know if this is simply a mathematical device or it has some.
Well, I'm trying to avoid such transformations. They are very interesting, by the way. If you look at gravity values, are squared or something. The problem is that if you resist from having not only locality but also unitarity, then at first sight amplify the violent unitarity. Then we can make some parallel transformation, see, well, maybe it has to maybe it preserves unitarity, but that often it does that if you are able to transform the whole thing away. So if you are able to transform things back to the Einstein-Hilbert expression, of course, that thing obeys unitarity in the provincial sense. Provincial in the sense that, of course, the thing is not renormalizable. So it does have all the difficulties in the far ultraviolet, including the difficulties with unitarity. So the same thing is unitarity, well, up to a point. And if you make transformations, the diseases of the theory will show up somewhere else. People make transformations all the time, and then the theory looks more unitary in one frame than in the other. Because in other frames you have difficulties with renormalization, with random costs, and so on. So the theory is not completely unitary no matter what you do, because you haven't understood the theory yet well enough.
Thank you very much. Okay, and this time for the speaker.